This is presentation video on our project on DDQN-based task offloading in mobile edge computing, and we are Group 10. Mobile devices are increasingly required to handle complex applications, but their computing resources are limited. Mobile edge computing provides a solution by offloading tasks to nearby edge services. However, in real applications, tasks are not independent. They often have dependency relationships, which can be modeled as a dodge. Therefore, we need to optimize both delay and energy under those constraints. In this project, we model tasks as a directed acyclic graph. Each task can either be executed locally or offloaded to the edge. Our goal is to find an optimal scheduling policy that minimizes delay and energy consumption while maximizing overall QoE. This figure shows an example of a dodge. Each node represents a task, and edges represent dependencies. Tasks must be executed in topological order. This makes the scheduling problem more complex compared to independent tasks. In merge system, tasks can be executed locally or offloaded. Local execution avoids communication overhead, but may be slower. Offloading reduces computation time but introduces transmission delay. So there is a trade-off between computation and communication. We evaluate performance using four metrics: delay, energy, completion ratio, QoE. QoE combines multiple factors and is used as the overall performance indicator. We compare our methods with two baselines. The first is all local execution. The second is a greedy algorithm, which selects the faster option for each task. However, greedy does not consider long-term effects. To address this, we use a double deep queue network. The state includes task and environment information. The action is to choose local execution or offloading. The reward is based on delay and energy. Through interaction with the environment, the model learns an optical policy. This figure shows the training process. We can see that the rewards increase over time and gradually converge. This indicates that the model is learning an effectively scheduling strategy. This figure compares DDQN with the greedy method. We use log scale because the differences are large. We can see that DDQN significantly reduces energy consumption. It also slightly improves delay and greatly improves QoE. From the results, we observe that completion ratio is small, energy is significantly reduced, delay improvement is moderate. The large improvement in QoE is mainly due to better energy efficiency. There are still some limitations. For example, throughput is slightly reduced. Also, the merge environment is simplified. However, the results show that reinforcement learning is effective for this type of problem. In conclusion, DDQN can effectively optimize task offloading in merge systems. It achieves a better balance between delay and energy, and significantly improves QoE. This is our implementation in Google Colab, and also we have uploaded it to GitHub and included the link at the end of our report. Now we can run it all, and we can wait for some seconds. First, we take some definitions and the algorithm and the model and the environment setup. Next, we try to define the agent, which is DDQN based. And the detail of this evaluation will show on our report about these equations. Here we can show the training curve and the final result. We can see that the DDQN outperformed on greedy methods. That's all. Thank you for your attention.